Hello, I am Ram Kumar from the Power Delivery team inside Industrial Systems. In this presentation, we will look at the working of the isolated 48 volt to 400 volt bidirectional DC-DC converter reference design TIDA00951. Bidirectional converters use the same power stage to transfer power in either directions in a power system. For example, a single DC-DC converter can take power from a 400 volt DC bus and use it to charge a 48 volt battery, and under certain conditions can take power back from the 48 volt battery and feed it into the 400 volt DC bus. A use case of this approach is shown below. Here we show the block diagram of a traditional UPS. A separate AC-DC charger is used to charge the battery from the AC mains, and when the AC mains fail, a DC-DC boost converter takes power from the battery and feeds it into the 400 volt DC bus. An alternate approach would be to use a single bidirectional DC-DC converter which is capable of taking power from the 400 volt DC bus and charge the battery, and when the AC mains fails, can take power back from the battery and feed it into the 400 volt DC bus. We now look at an overview of the TIDA00951 reference design. The TIDA00951 is a 2 kW bidirectional DC-DC power stage which is controlled through a C2000 controller. It works as an active clamped current fed full bridge converter capable of delivering 2 kW power during the backup mode, and as a voltage fed full bridge converter which can deliver up to 1 kW power to the battery in the battery charging mode. In both the directions, it achieves greater than 94% efficiency due to soft switching. Switching at 100 kHz, this design is compact and comes with inherent overvoltage, undervoltage, overcurrent protections. In the backup mode, that is when drawing power from the battery and feeding into the 400 volt DC bus, the power stage works as an active clamp current fed full bridge converter. In this mode, the low voltage MOSFET achieves zero voltage switching or zero current switching at turn on, and the high voltage MOSFET always achieves zero voltage switching at turn on and turn off. Apart from this, the dI by dt on the high voltage MOSFET at turn off is reduced, resulting in lower reverse recovery losses. The use of a current fed converter structure results in reduced ripple current as seen by the battery, and it also helps in achieving wide input and output voltage range operations. Traditional current fed converters suffer from high voltage spike on the low voltage MOSFETs at turn off. The presence of the active clamp circuit controls the peak voltage spike on the low voltage MOSFET to less than 75 volts even at 60 volt battery input without using any additional passive snubbers. The active clamp circuit also helps in realizing zero voltage switching at turn on the low voltage MOSFET. In the battery charging mode, that is when drawing power from the 400 volt DC bus and charging the battery, the system works as a voltage fed or a phase shift full bridge converter. The low voltage MOSFET operate as synchronous rectifier and therefore achieve zero voltage switching at turn on and turn off. The presence of the current fed inductor here reduces the ripple current as seen by the battery. The peak voltage spike on the low voltage MOSFET is again limited to less than 75 volts. By using the phase shift control, the efficiency can be further improved due to reduced switching losses on the high voltage MOSFET. We now look at the efficiency results of the system when operating in the backup mode. The system achieves a full load efficiency of greater than 94% at 48 volt nominal battery input voltage, and the efficiency goes to above 95% at 60 volt battery input voltage. Overall, the high efficiency helps in reducing the thermal management while increasing the battery backup time provided by the system. In the battery charging mode, the max charging current is limited to 16 amperes by the firmware. It can be seen that the efficiency at full load when the battery is at its nominal voltage of 48 volt is as high as 94%, and it goes up to 95.5% when the battery voltage reaches its peak value of 58 volts. The high efficiency achieved during the charging mode is important as it reduces the power drawn from the AC mains. We look at some of the critical operating waveforms in the system. In the boost mode, while operating as an active clamp current-fed full bridge converter, the low voltage MOSFET achieves zero voltage switching at turn on for medium to high loads. The waveform on the right shows this. It can be seen that the MOSFET drain to source voltage falls to zero before the MOSFET is turned on. The range of input currents for which the ZVS operation occurs depends on the value of the leakage inductance. In the TDA00951, the leakage inductance is measured to be 250 nanohenry. This results in ZVS operation for any input current greater than 15 amperes. The image on the left shows a slightly zoomed out waveform. It can be seen that the MOSFET turn-off voltage spike is very limited. This is achieved due to the presence of the active clamp circuit in the system. In the backup mode, when the input current is less than 15 amperes, the energy stored in the leakage inductor is not sufficient to create zero voltage switching. Under this condition, it can be seen that the drain source voltage across the low voltage MOSFET shows a valley. The image on the right shows the current through the MOSFET at turn on. It can be seen that the current through the MOSFET almost reaches zero at turn on. So even when the zero voltage switching condition is not met, the low voltage MOSFET is always turned on at zero current switching. This helps in reducing the switching losses at turn on, irrespective of whether ZVS is achieved or not. In this slide, we look at the battery charging mode operating waveform. In the battery charging mode, the high voltage MOSFET works as a voltage fed full bridge converter and the low voltage MOSFET works as a synchronous rectifier. Since the low voltage MOSFETs are turned on and turned off under ZVS condition, and since they are working as a synchronous rectifier, the overall switching and conduction losses in the system are reduced. The ZVS turn on and turn off operation of the low voltage MOSFETs can be seen from the trace here. The blue waveform shows the current through the current fed inductor, which is working as a filter inductor in this mode. This slide shows the mode transition waveform when the system moves from the battery charging mode to the backup mode. Initially, when the DC bus voltage stays above 380 volts, the system stays in the battery charging mode. And when the DC bus falls to around 370 volts, the system moves from battery charging mode to the backup mode. The time taken to move from the battery charging to the backup mode is less than 100 microseconds and is typically around 80 microseconds in most cases. Once into the backup mode, the system stays in soft start until the point that the DC bus voltage falls to 360 volts. At this point, the system moves into a full boost power mode and tries to regulate the DC bus voltage to 370 volts. With this, we come to the end of the presentation today. For further information on this TI design, please refer to the following link. Thank you.